All right, hello, my wonderful students. This is part 2 of Foldable number 3 for 7576. The last one we just did was modeling with an exponential equation, and this one's going to be using a natural logarithm. Okay, so this one, flatten this out a little bit. This one says a spacecraft can attain a stable orbit 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second or more. So the formula for a rocket's maximum velocity, v, in kilometers per second is v is equal to negative 0.0098 t plus c times the ln of r. The booster rocket fires for t seconds, and the velocity of the exhaust is c kilometers per second. This basically means the velocity of the exhaust. If you look at a rocket fire off, you see a bunch of smoke come off. That's the exhaust. So the velocity of all the exhaust coming off the rocket is what it's talking about. Okay, so the ratio of the mass of the rocket filled with fuel to its mass without fuel is r. So the mass of the rocket when it's full of gas, basically, and then versus the mass of the ratio of the rocket when it has like no more fuel in it. Okay, suppose that the rocket has a mass ratio of 25 and firing time of 100 seconds and an exhaust velocity of 2.8 kilometers per second. Can the spacecraft attain a stable orbit at 300 kilometers above Earth? Well, let's find out. So first things first, we have our equation, which is v is equal to negative 0.0098 t plus rc times ln of r. And now what we have to do is we have to go ahead and find all these variables, right? And they're all in here. The first thing we have is that the rocket has a mass ratio of 25. That means our ratio R is going to be equal to 25. Then we see that firing time of 100 seconds. That means our T is going to equal 100 seconds. And last but not least, we have our exhaust velocity of 2.8 kilometers per second. That means our C is going to be equal to 2.8 kilometers per second. So now we can go ahead and put all these values into our equation over here. We'll do that in, we do it in blue and red. So we have our V is equal to negative 0.0098. And then we have our T, which is 100, plus our C, which is 2.8 times our log of 25. And now it's just a matter of plugging this into the calculator and seeing what happens. So, well, this one we don't really have to. So if we were to do this, we have equals. Remember, this just moves it over 2 decimal places, so this ends up being negative 0.98. But this is what we will plug into the calculator, so it'd be plus 2.8 times the natural log of 25, which is approximately 3.219. And now we can go ahead and say our V is approximately 8.0, because that's what happens when we plug it into the calculator. And now we can go ahead and write our statement. I'll start up here. So the maximum velocity is 8.0. And remember, we needed to be sustainable, it had to be over 7.7 And it is, because it's at 8.0 km, kilometers per second. So that's good. So which is greater than our 7.7 kilometers per second that was needed to not to, I'm going to say for a stable orbit. Okay, so that means therefore the spaceship can attain a stable orbit. And let's just keep it 300 kilometers above Earth. It's every bit of this piece of paper. Okay, I know it's a lot of writing, and we should probably box this up a little bit just so we don't get confused. But I needed to make sure it all fit, and it barely all fits, so there it is there. And don't forget, this is using a logarithm or natural logarithm.